These are the notes for AP Calculus on the topic of polar equations, and we're going to look at some advanced area problems. So we've got the same formulas we've been using for polar equations. The primary one we're focusing on today is just the area with one polar equation right here, where it's 1/2 is equal from A to B, where the area is enclosed between theta equals A and theta equals B, and we've got the radius squared. All right, so this first one says the figure above shows the graphs of the polar curves r equals 2 cosine 3 theta and r equals 2. What is the sum of the areas inside the circle but outside the 3-petal flower? So if they're inside the circle but outside the 3-petal flower, we're talking about these areas right here. And the sum of all of these. So I'll just shade in kind of what we're finding the area of. Okay, so in general what we can do is we want the area in the shaded area. We can take the area of the circle and subtract area of the 3-petal flower. So, or another way of saying that, you take the area of the circle and then subtract, since we've got 3 petals, we can do 3 times the area of 1 petal. So that's what we're going to do. So notice our circle has a radius of 2. So the area of a circle is pi times the radius squared, in this case 2 squared, minus 3 times, with polar coordinates, the area. We just have one curve with the flower, r equals 2 cosine theta, would be 1/2. And then we've got the integral. And the toughest thing to figure out here is what the lower and upper limits for the integral would be for one of those petals. So what you can do is we know for sure the petal, one of the petals starts and stops right there at the origin. And at that origin, we don't know the angle, because really any angle could give you that if the r radius is 0. And that's the key. We know r has to equal 0 at that point. So we can take our equation here and substitute in 0 for r. And let's go ahead and solve that to figure out where a petal would start and stop. Okay. So to solve this one first, you could divide by 2 to isolate the cosine. 0 divided by 2 just gives you 0 equals cosine of 3 theta. And just think, where is cosine equal to 0 on your unit circle? Well, cosine of 0 is right here, pi over 2, and right here, 3 pi over 2. Remember, cosine is the x-coordinate, and that's 0, 1, and this point is 0, negative 1. So, I notice it's 3 theta that would have to equal that. So the 3 theta that's inside cosine should equal pi over 2, or 3 theta should equal 3 pi over 2. So if we divide by 3, well, instead of putting divided by 3 there, which is also more complicated, fraction divided by 3, remember dividing by 3 is the same as multiplying by the reciprocal of 3 is 1/3. So that gives us theta equals pi over 6. And the same thing here. Divide by 3, which is the same as multiplying by 1/3. Here you can see the 3's reduce out, and you're just left with pi over 2. So those would give us our lower and upper limits of one of the petals. Now we don't necessarily know which petal it is. If you needed to know, we don't, but if you want to know which petal that's actually given you, in this case they're all the same size, what you could do is substitute an angle between pi over 6 and pi over 2 to be easy, like pi over 3 would be a good choice since there's a 3 inside there. So if we let r theta equal pi over 3, you don't have to do this part, this is just showing you how you can figure out which petal it is. So you'd have r equals 2 cosine. When you plug in pi over 3 here, the 3's reduced out and you're just left with cosine of pi. The cosine of pi is negative 1, so you get negative 2. So pi over 3 is about 60 degrees right here. And negative 2 means you go the opposite direction 2. Notice that takes us to right there. So this pi over 6 to pi over 2, where r0 is actually giving us this petal of the flower. But we didn't need to know which one it was. That's just if you want to know which one I was giving. And then, of course, our formula says this, we have the radius, which is right here, with this curve squared. So it'd be 2 cosine 3 theta squared times d theta. And then this is with the graphing calculator. So far we haven't used it, but now we need to in order to integrate that. So I'll show you guys on both calculators how we do that. So let's start with the 83 or 84. So in mode here, just make sure it's in radians. And you don't have to have it in polar, but it makes it look more like what we have on paper here if you do have it in polar. Let's quit out of there. And then let's just type in, we've got, that's 2 squared is 4 times pi, so we have 4 pi. Second pi. And then minus, this becomes 3 halves. So 3 divided by 2. And then times the integral, so math number 9, function integrate. And then we've got parentheses here because we've got to square this whole thing. 2 cosine of 3. If you have it in polar mode, it'll say theta there. If you have it in regular mode, it'll say x, and that will still give you the right answer. As long as it's the same function. And then close parentheses, so we want to square that whole thing. Comma, our variable is theta. Comma, the lower limit is pi over 6. 6. And then comma, the upper limit is pi over 2. So we end up with an area of 9.425. Or if you want, you could put units squared, but you don't have to. It's not specific units, just to remind yourself it's area. And then on the inspire, so it looks like, is just document, insert calculator, we already have here. And then menu, calculus. Oops, actually, let's before we do that. So we had 4 pi. And then minus 3 halves. There we go. Times, here's our definite integral. Pi over 6. To pi over 2. open parentheses, 2 cosines on the trig button, cosine 3 thetas on the same button as, oops, sorry about that, on the same button as pi. We put the squared outside and then d theta. We get the same answer. All right, let's take a look at the next example now. Okay, next one, a little bit different. So we've got let R be the region in the first quadrant. Bounded above by the graph of R equals cosine theta, and below by the line theta equals 1. So this looks like a normal polar graph. The theta equals 1 is an interesting one, though, because what that produces, if you have a constant angle, this is 1 radian, it actually produces this straight line right here. So this right here is theta equals 1. Because what that's doing, that's 1 radian. Notice up here we've got pi over 2. We're in the first quadrant, so it's somewhere between 0 and pi over 2 here. Theta equals 1, because pi over 2 is like 3.14 divided by 2. That's like between 1.5 and 1.6 radians. Remember, radians don't have to be in terms of pi. They're just often written that way. They're just numbers here. So theta equals 1 would be about right here. And notice that the angle is constant, so actually the line would keep going forever both directions, but we're only looking in the first quadrant in this region. Notice there's no r in the equation, this polar equation. So the radius could be anything. So if the radius can be anything, but the angle is the same in polar coordinates, that's what produces a linear equation. Theta equaling a constant. And then that means the curve here, this curve is the r equals 5 cosine theta. Okay. All right, and it asks us, what is the area of R? All right, so theta equals 1 is kind of like on our regular graphs in Cartesian coordinates when we had like a vertical line where it was like x equals 1. And if our region was over here, say, that could be like the upper limit. Or sometimes it could be the lower limit. So when you have that, just like x equals 1, this is either going to be the upper limit of our integral, or the lower limit, one or the other. So how we can tell which one it is by noticing where these intersect right here. Again, we can tell there. This is hard to tell where it is, but this one we can tell. Again, the radius has to equal 0. So if we let 0 equal to this, we'll see where they intersect. And we won't know whether theta equals 1 is the upper or lower limit. So if we set 0 equal to 5 cosine theta, divide by 5. 0 divided by 5 is 0, so 0 equals cosine theta. So we're looking for where cosine equals 0 again. And the first place that's true is that theta equals, pi over 2. So since that's where they intersect there, theta equals 1 is stopping the graph right there. Well, what's bigger, 1 or pi over 2? Well, pi over 2 is about, again, approximately 3.14 divided by 2. So you can see that would be 1.5 something, not quite 1.6. So that's larger than 1. So that tells us that in this case, theta equals 1 is going to be a lower limit. So when we set up our integral, it would just be 1/2 integral from 1 to pi over 2, and then 5 cosine of theta squared d theta. And again, we just have to use our calculator, so I'll show you guys on both calculators how to enter that in. There we go. Sorry about that. All right. So we've got 1/2 on the outside, so you can go 1/2 or just 0.5 times math number 9, function integrate, open parentheses, 5 cosine theta, close parentheses, on the cosine, another close parentheses, so we can square the whole thing, and then comma, theta is our variable, comma, lower limit is 1, comma, upper limit is pi over 2. And we get 0.7259, so you can write to thousandths place, it'd be 0.726. And let's use the inspire now. So you just put 1/2 or 0.5 again if that's easier, times integral from 1 down to pi over 2, again open parentheses, 5 cosine, oops, sorry about that. I clicked a little too fast for it to handle here. There's cosine of theta. Sorry about this. I'm clicking too fast for the program here to handle. There we go. Squared, and then d theta. Okay, and enter. I get the same thing. Sorry about that. I took way too long. All right. Last one here. This last one, the calculator is not really helpful. So it says let R be the region in the first quadrant, bounded by the polar curves R equals theta and theta equals K, where K is a constant. Remember what we said, theta equals a constant, like that other one with theta equals 1, is just going to produce a linear equation. So this one, right here, this is theta equals K. This time the only difference is we don't know what that angle is yet. What we do know about it though is it's got to be somewhere between 0 and pi over 2. And we want the area of R in terms of K. Remember what that means? We're not going to get a specific number like we did on the last one. We're going to answer based on what K is. So on this one, again, we note to see if this theta equals K, just like the other one, this is either going to be our upper limit or the lower limit. One or the other. Theta equals K. All right. So the way we can tell, just go right here. Again, we know the intersect right there. That's where R equals 0. We can't tell where this other intersection is. So here, if we set R equals 0, in this case, notice it's already solved. You get theta equals 0. This time we're comparing 0 and K, and since we know K is larger than 0, it's between 0 and pi over 2, this time K ends up being our upper limit. So I set up the integral to be 1/2 for the area. Integral, the lower limit is 0. Upper limit is K. And it may seem weird, but our equation is just theta. So it's theta, but that gets squared times d theta. It may look weird, but this is really just like integrating x squared dx. It's just a different variable. So we just integrate this part by hand. Can't use the calculator because we don't know what k is. We want area in terms of k. So when you integrate theta squared, you get theta cubed over 3. This is evaluated from 0 to k. 1/2. And you substitute in k for theta, be k cubed over 3 minus, when you substitute in 0 cubed, that's just 0. So simplify, that just becomes k cubed over 6. So that would be our area in terms of k. What this tells us, if we knew what that angle is, let's say theta would equal 1. Well then, if theta equaled 1, then we'd have 1 cubed over 6, our area would be 1/6. Or if theta equaled 1/2, we'd have 1/2 cubed divided by 6, and so on. And that concludes the notes for AP Calculus on the topic of polar equations with advanced area problems.